and our last speaker for the first session is going to speak to lunar photoemission yields inferred from ARTEMIS measurements.
Hi, I'm a scientist from the Space Science Lab at UC Berkeley. My name is Shaozhe Xu. So a brief introduction to the photoemission yield, which is the number of emitted photoelectrons per incoming photon. So this is one of the fundamental properties of the solid materials. Here is the lunar surface. There are lab work determine this number for energies below 20 eV, but not yet constrained for higher energies. So the high energy tail of the photoelectron distribution can be important as the surface potential varies drastically in different plasma environments, and also when the solar photon fluxes, for example, during the solar flares, that will enhance the high energy contribution too. So to better characterize the surface charging, we need a better constraint on the photoemission yield at high energies. So that's the motivation. Let's see if it works. Oh, okay. First, this is case study showing the lunar photoelectron observation from the ARTEMIS mission. So to the right is a time series of observations. If you look at the circled region, which shows the electron energy spectra for parallel and anti-parallel electrons, there's a distinctive line at roughly 4 to 500 eV. If we plot the spectrum themselves here, you can see the parallel and anti-parallel, it has a peak at 400 something eV. So this is a feature of what we call OJ electrons, which is the ionization, a result of ionization of inner shell electrons. So it has a fixed energy, which is around 500 eV for atomic oxygen. So this is actually a unique feature to identify lunar surface photoelectrons. And we believe this is the first report of oxygen OJ electron observed by a spacecraft. So using this feature, we are able to identify one case when the moon is in the magneto-tail lobe, which is shown here, and 3 other cases when the moon is in the solar wind. To calculate the photoemission yield, it basically comes from this equation, which is to say the photoelectron flux is a function of solar irradiance, the yield, and also a probability function. So the probability function is to say the distribution, the probability distribution of photoelectron flux as a function of electron energy produced by a single photon energy beam, single energy photon beam. So if you integrate that over different photon energies, that give you the integrated photoelectron fluxes. So that's what this equation is. So now photoelectron flux is measured by ARTEMIS, and then the solar irradiance provided by solar irradiance model FISM 2 here. And if we know the probability function, we can solve the photoemission yield by doing a matrix inversion. But you see, I highlight this probability function in yellow because this function is only measured in the lab for less than 20 eV. but it's unknown at high energies. So in the literature, people came up with a few different functions, but actually it's not well constrained. So in this study, we use three probability function in the literature and also the delta functions to constrain the calculate the yield. So for the 5 assumed probability functions, we have this result where we show the photon energy versus yield. The triangles are lab measurements of the yield where is only for less than 20 eV. You can see the yield increases in energy then falls off. If you look at this curve alone, you assume the yield just decrease in energy. But what we calculated are the colored symbols, red for low lunar surface potential, and blue and red are for different lunar surface potentials. Actually, our results show that the yield actually remains roughly constant at high energies, roughly at 0.01. Although there is one order of a scatter in the yield. Those thing now is solved, but like I just introduced, we actually don't know the probability
2
function.
minutes.
Yes, thank you. So we did a sensitivity study with the delta function, which is to say a single photon beam will produce only one energy photoelectrons. So conceptually, smaller the x is, which is to say a 10 photon EV, 10 EV photons can produce more 1 EV photoelectrons than 5 EV. So smaller x is gives you a higher yield. So we can determine a lower bound in yield of 10 to the minus 3, but it does shows a scatter over 3 to 4 orders magnitude in yield. In the literature, the R yield determined for metals, which is 0.1. So if we use that as constraint, we can kind of lower down this uncertainty to 2 orders of magnitude, but still is a big uncertainty there. So quick summary, we make the first report of oxygen object electrons at the moon by the ARTEMIS spacecraft, infer a lower bound of 10 to the minus 3 in yield. And also, but the uncertainty is over orders of magnitude because probability function is unknown, which motivate future experiments on the lunar sample for better characterization. So that's all. Thank you.
Thank you. So I have a question. How would this impact using electronics on the surface, or does it have any impact? And do you foresee any effect of the solar cycle on these measurements?
So for measurement for solar cycle, during solar max, the solar irradiance have more high energy photons. So actually that will make the high energy photoelectron tail more important than usual. So it's more critical to determine the CO during solar maximum. So what's the other part again?
Oh, does this have impact on electronics that are being used on the surface?
I don't think so. It's more so that the surface environment is different because of this high energy tail. It's if we know the yield better, we can better characterize the lunar surface environment. So that's kind of indirect inference, if that makes sense.
Okay, but so what would be the larger impacts on the lunar exploration?
Um, uh, I think right now we don't have a very good surface potential model for different environments because of this yield is unknown. So if we have a better characterization, we can provide a better prediction.
Okay. Okay, so a question came in the chat that said, can the effect be used to find water or other materials? So that's kind of what I was getting at. Thank you.
Oh, sorry. Um, One thing you can do is actually to use the OJ electron feature. To It will have a fixed energy at different for different species. Theoretically, there are spectrums showing the different peaks at different energy for different species. But that does so you theoretically, if you measure those peaks, you can understand the composition. But it does require very fine energy resolution measurement on the lunar surface.
Okay.
Yeah, I hope that answers the
Okay.
question. Mhm.
Yeah, it did for me. Thank you.
Great.
All right. Thank you